Thanks. So thanks for the invitation and to be able to come here. Some amazing things being done here. I'm really, it was well worth the trip to find out what's going on here. The 2035 effort is really very parallels a lot with what our institute seeks to do as well. Oh, this is a wonderful one. It's going to reboot my computer in the middle of my lecture. That would be... So I'm going to start off telling you a few things you know, and then I'll tell you some more things you already know, but I'm going to tell them to you differently. And the difference is going to be the important part of how we do this. I'm also going to be asking you questions. You're going to need to have your cell phone or computer out to participate in the polling, because that's the important part of committing yourself to an answer to see how things go. So this is the stage. We know this stage. One of our futures follows along one of those lines. And as I said there, a hint, we've already missed the lower blue one. And we're seeing the consequences of the increase in global warming. We're seeing the frequency of disasters, flooding, and droughts, and so forth. So it's here. It's part of our life now. And we need to figure out what to do about it. But the first thing I would argue what we need to do about it is to think about how much we really understand what we can do about it. And so I'm going to be asking you a few questions as we go through here. This little scan cube will always show up, so you'll see it some more times. But first is, how do you really feel about climate change, right? You see the slide, this is what's going on. You're in the audience, so you must have some interest in this. But when it comes down to it, you know, if you chose amongst these, what would you choose, what choice would you make in terms of how you see, how you view your own feelings about what's happening? I would assume not too many people are dismissive in this audience. Everybody been able, now you really do need to try and do this. There are going to be a few more questions. It's going to be important that you participate in this so we get some answers. And for this one in particular, I'm going to show you how others in more scientific surveys than this room have looked at this question.
There could be a bias in the audience.
There could be a slight bias in the audience. So based on what we have here, a lot concerned, not only a quarter alarmed, and nobody dismissive. Well, that's good, because I'm pretty sure dismissive means you dismissed and noticed about this talk. National estimates track pretty well with what we see here. A high amount of concerned, a little bit more in the alarmed, but again, they're not picking an audience which has come to hear a talk about this. And if you look globally, so that one was nationally, if you look globally, these are different words that they use to describe here. The young people are both sad and afraid and angry. This last one, though, powerless, is one that really is the one that I want to pull out of that stack of things, feeling powerless. And I'm going to try and convince you you're not powerless, that there are things you can do and things you can figure out to do. Now, technical people in the room who are coming up with renewable energy scenarios, with reducing power consumption, energy efficiency, your institute, right? A big part of this, of course. But this is something that's written out by people who sit down on the table, think logically about how we're going to get there, they map it out, but that doesn't mean people do it. And so this is what we come up with in 2017 of how we're going to get there. And look at this, we're already a couple years out, it's going up. COVID hits, it goes down, but boom, it bounces right back up. And so when you think about all the information that we had, it's not penetrating. We have, all these COP events, and Eric, I think you were saying, you got a slide just like this, where here are the emissions, they're going up, and they're all the cops and they're not doing it. And some of the reasons, the contributors are that, not because we don't know how to do it or what's needed to be done. Some people just don't want to do it. They don't believe it's important to do that. And so that's where knowledge and policy change starts to come into this. If you look at fossil fuel energy use across the planet, it's going up. And more importantly, energy use per person. Even if we normalize for changes in population around the world, energy use per person is going up. So if you base the energy consumption on fossil fuels, you're never going to go in the right direction. So how much of this can we look at in terms of renewable energy contributing to this increase? And we're going to get to that slide later in the talk. This is construction globally. And so, again, this is a global problem. We have to think about all the things we can do globally. So some of the solutions you come up with will be great, but not really able to be installed, shall we say, unless other countries get into this with us as well. So let's look at what we're going to do. We're going to talk about how we need some education in a way that's different, because we're doing the other things that's not working. We got to try something different ways to talk about it, learn about it, present about it. We need to effectively communicate and find easier ways to communicate. And I'll be telling you what I've learned from talking to social scientists about how to communicate on topics like this. And then, the very personal part of this, do my choices matter? Am I powerless? Can I do something about this? So when I look at this, I think about, okay, we have a product, right? That's good engineering. We want to make something. So what do? Well, we did the science, we did the fundamental research that came out of that led to innovation, that led to production, and we got our product. Okay, so that's how we get from that to our product. If our product is less than 2 degrees C or less than 3 degrees C, how do we get to that product? Well, we're going to need infrastructure changes, which are going to require policy changes, which are going to require basic science, and that science also includes not just technical, but social and educational solutions. So I looked and thought about other things that have been very, very difficult and very globally a problem, something like smoking. So smoking was addressed, right? Many years ago, your dentists and your doctors were saying, these are the best cigarettes, you'll really love this. Okay, and then, well, maybe not so much. Put these really quite glaringly accurate statements on these, and people still smoked. They still will buy these. Smoking gills, yeah, whatever, not me. Policy changes occurred. You could not smoke in a bar. You could not smoke in your office. You could not smoke in the grocery store. You could not smoke, my favorite, on the plane. This is the smoking section in the back. And here, 2 rows ahead of that, that was the no smoking section. So this education was not sufficient, but it was necessary. And that's, I think, where we are. We have to go back and say, no, we're not educating enough about the situation and communicating. We're also seeing sometimes where it doesn't work, predetermined views. And I say, you go into a McDonald's, and I don't care if you put how many grams of fat or calories are on this thing. When you walk into a McDonald's, you're buying the Whopper if you want the Whopper. Or
that's Burger King.
Oh, so Burger King, sorry. Oh my gosh.
The Big Mac.
I went into the wrong fast food restaurant. How do you even know that? No, okay. So, because your mind's already...
I'm a vegan, by the way. So.
Yeah, okay. So, but really, by that time, your mind's made up. And so you have to... But people know there are calorie labels now. They know they can look. They can make decisions with that information. We don't have that with carbon, with energy. I also I talk to people about eating, and they say, I say, one of the problems is we overeat, and that wastes a lot of energy and releases a lot of carbon. And so when I teach a course on this, I say, well, how many calories do you think you lose if you run a mile? And because a lot of people try and work it off. Well, I ate that Big Mac or Whopper or whatever, but I'm going to run a couple miles when I get home. Yeah, it's 100 calories a mile. The average American eats between 3,000 and 3,600 calories a day, because if you eat out, this is kind of your diet. You have breakfast, lunch, and dinner. There you are, 3,400 calories. It's not hard to get to. That's a lot of miles to run to get through that. So information is not sufficient, but it's necessary. We need to use that information and start to think about, can we put labels on things? Can we increase awareness? And can we create sort of this shared environment locally, nationally, and globally about what we need to do to address this? One of the things that we can do at universities is start to educate people who are going out into the workforce, so when they make construction decisions or they make purchasing or building decisions, they understand what the implications of that are. So I say to my colleagues who are professors, I say to the students who might become professors, I say to the students who might become in business and want to be able to advise within the business on energy and carbon emissions, to think about things in a little bit different way that I'm going to try and do. Anyway, this is just the course that we teach to the faculty. I actually gave Eric McFarland my course notes for this. If you want to teach a course like this or just integrate parts of this, we cover batteries, energy use, automobiles, transportation, cement, steel, the usual stuff, but from a sort of a calculating and energy input perspective. A lot of that course we talk about modeling, because making projections, whether it's in business or in climate or in energy use, you see these predictions and we try and teach the students to do them and see, well, are they accurate? In 2020, what did we say in 2010 was going to happen by 2020? If you do a trend analysis, did you get it right? So that's another part of the course, and thinking about how fast or wind or solar could go, and then talking about what might prevent that, what might enhance that, what might help that. That's all part of the course. So now let me jump into more how are we going to communicate this, how are we going to do this. So I talked with social scientists and they said, okay, first of all, the numbers have to be comprehensible. No exponents. Okay, engineers? Okay, yeah, sure, we understand exponents. So scientists, yeah, we get it. How many, planets there are in the universe or something. No exponents. Units we can understand. If you spend money in dollars, you understand it. If you spend money in, I don't know what your currency, euros, maybe you sort of understand it, or it's close, but what about yuan or RMB or something like that? And people have to relate to the number, even though it's a simple number. It has to mean something to you. So, things like, so 0 to 100, no change in units, and do not add or remove zeros. You're going watts, kilowatts, gigawatts, megawatts, and everybody's like, mega, is that bigger than a kilo or a giga? So keep it all in small numbers. Things like the US, well, they report quadrillion BTUs, or maybe 106 exajoules. I mean, you can't, on any scale, fathom what that means. Same thing with carbon, 33 gigatons. I don't know what a gigaton is. And so even some of these solutions, by drawdown solutions, they're great solutions. There are a lot of good ideas here, but then they give you a table and they say, well, reduced food waste is 87 times 10 to the 19th tons. Okay. So what are we going to do? We're going to start with a baseline, and that baseline I'm going to define energy, calories. Yes, calories is a baseline. But you're already starting from a handicap because an American calorie is a kilocalorie. So our capital C calorie is a kilocalorie, which is so 2,000 calories is 2 million real calories. Start with food energy as a baseline, and then compare other energy units to that. Same thing with carbon emissions. Start with the food, your combustion engine. You combust what you eat. Start with you and how much CO2 comes out from that. And then think about how we relate those calories to things that we use, like this one, 2,000 calories. How many light bulbs could I power continuously on 2,000 calories? Okay, so here comes your second one. Come on. Oh, wrong clicker. There we go. Is it 1? Is it 2 to 9? Is it 10 to 50? Or is it greater than 50? I've seen students take out calculators. They're starting to calculate. I don't want to do that. It's like just an intuitive thing. It's trying to test your, I think it's about this or that. Ready? Eric knows the answer because he told me today. So I'm going to have to -1 from all the other answers. Okay, here we go. So the winner is 10 to 50, 100-watt light bulbs. The loser is greater than 50. Okay, that's good. Well, and this proves my point. Right, Eric? Fact check. Fact check. Okay, I got a fact check. Right. What this tells you is that you think food has a lot of energy, but when you turn on a light or you do certain things, you don't really know how to equate that to the energy that you think is a lot, right? And I kind of led you down the path because it's like food energy, 1 pound. You're thinking, oh, I got to go so far to lose a pound. That's a lot of energy. But actually, a 100-watt light bulb, try and touch one of the old, inefficient 100-watt light bulbs. You burn your fingers something really well. So 100 watts, 24 hours, 2,400 watts, about 2.4 kilowatts. So the actual number is 2.32 kilowatt hours. So about, for purposes here, 2 kilowatt hours is about equal to your food. 2 kilowatt hours. If you could eat gasoline or electricity, you could live on like 10 to 20, 30 cents a day. That's how cheap energy is relative to the food energy. The second part of this is how much CO2 do you release having eaten 2,000 calories a day? This is going to be our baseline. We're going to relate everything now that all the CO2 emissions, we're going to relate to this daily CO2 emission from our food. Because when you take away all the technology, all the horses, all the things that we use to help us do the things we do, you get back to just 8 billion or 9 billion people breathing and 8 billion, 9 billion people eating 2,000 calories a day, even if they have no other things to help them do that. Ooh, it's almost a tie. Oh, wow, a three-way tie. Look at that. The answer is about a kilogram, a little less than a kilogram, a kilo. That's a surprising number. I mean, it seemed large to me, and I calculated, checked it. It's about 2 pounds a day. So I take that now as this baseline of 2,000 calories. I'm going to call that one daily energy. The number is 1. That's not a big number. It's not a small. It's 1. 1 daily energy, 2,000 calories. 2 pounds of carbon that comes from that, that's 1 daily carbon emission, which, by the way, 2 pounds of carbon, you need about 15 trees to absorb that. So you want to of course, CO2 goes other places, the ocean and other places, but 15 trees. Oops, wrong button. So this is the basis of how I want you to, I'm going to go through some numbers now, but we're going to go through the perspective of daily, per person, energy and carbon emissions. So first let's look in the US, how that plays out across the whole US, all the energy we use, and all the CO2 we emit from those non-renewable, non-fossil fuel things. And you come out with round numbers. They vary from year to year. I'll just use 100 D, 100 times that food energy. And for carbon, about 50. So about 100 to 50, 2-to-1 ratio. Now let's compare our energy use and carbon emissions, say, with China.
Bruce, this is you saying, I use 100 times the daily value of the energy that I intake?
No, so I'm saying that if you take all the energy across the US, as reported by the Energy Information Agency, you divide by all the people, that number is about 100 times a food energy unit. So
stuff I buy, places
it's all per person. It's 1D. All the gas, all the hydropower, everything, all the energy we consume, it's about 100 times the food energy for one person. But if you go to China, the per person number is about 34. So normalized to the Chinese population, about 34 times as much energy per person in China is consumed as in America. And their C number, ours is about 49, this is about 23. So if you look at the C to D ratio, how much carbon per energy, we're at about 0.48, where China's about 0.7. And why is that? The answer's in the slide. It's that big fraction of that's coal. And so that's a lot more carbon emissions for the amount of energy that you're getting from that coal. How about Denmark? What's really cool about Denmark is look at this purple one. That's their wind energy. And so they're getting a large fraction of their energy from wind. Well, a lot of electricity from wind, to be more precise. But look at their C to D ratio. It's almost exactly the same as ours. Why? Well, where they've got wind, we've got nuclear and renewables. We've got a lot more natural gas. They've got a lot more petroleum. So petroleum, again, not as energy efficient, especially for making electricity, as natural gas. Turkey. Why Turkey? I happened to visit Turkey, so I made this slide up for when I went to Turkey. But I was very shocked at this. Turkey has a lot of hydropower. I wouldn't have thought that. I didn't know enough about Turkey. I just didn't know that. And again, if you look at their bottom line, their C to D ratio is about the same as ours. So you have different ways of producing some of this renewable energy. But a lot of countries have about the same ratio, about a 2-to-1 ratio. But the more heavily dependent the country is on coal, the more that's going to shift.
Bruce, can I ask you a question?
Yeah.
I like this, but at the end, China is going to matter more than us because there's more population and that's per person.
Yeah.
Then I'm intrigued with India. Where does India fall in that formula?
But wait, there's more. Good point. And I point out India because where is a lot of globalization and of industry shifting to? It's shifting to India. India has a very low per capita C emission, but they're probably going to shift a lot to coal. And so in terms of climate and impact, they're going to be industrializing, but probably doing that a lot on coal. So this is like COVID. It's not a local problem, it's a global problem. You can't just solve it in your country and think the world is. You have to other countries have to get together and work on this as well. So again, this is sort of the summary of C to D ratios for a few different countries, and you can see a few more in this slide. And these numbers are easy to come up with. I chose that one because it was the biggest number I could find. Just a lot of carbon emissions per person there. There's also, if you've ever heard of the term virtual water, I call this virtual carbon. It's where your country says, well, we're not going to make steel. We're going to minimize use of cement. We're not going to do much international traveling. We're not going to industrialize much. We're just going to buy all the products from other countries. So you're essentially, and Belgium's the poster child on this one, because if you look at their base load and then their virtual carbon, they come up to 51C. This is a different year than the previous slide. I'm sorry about that. I only had this for 1 year. But the US in that year was 52, and Belgium, when you added in the virtual carbon, was virtually tied with the US. So you can claim to have a low carbon footprint because of your energy consumption, but it can be because you're importing that carbon.
Reminds me of everybody ordering from Amazon, because they think it's reduced. They don't have to go to the store.
Right, you didn't have to drive there to get it. Well, yeah.
But then Amazon, somebody delivers it to your house, so they use.
So the 2000 Watt Society said we need to get to about, we need to do 2000 watts, which would be 20D in my language. And they've refined that to say that 20D should be 15 renewable and 5 non-renewable. Think about where we are relative to getting there, and think about India, being at 5. It's a very impoverished country. This is 3C. India is at 5C. We want a world that doesn't have a lot of carbon, but we don't necessarily want to change a lot of things to get there. So we have to think about what we can do. So let's think about what we can do, or what people can agree to do. Stop smoking in restaurants, stop, doing certain activities. But it also requires that you understand kind of where your energy use is occurring. So everybody here is interested in reducing carbon emissions. What do you think is the correct energy use order? Energy. Does your car use more than your home, use more than the food delivered to your table? Okay, so that's the food system, not the food you eat, the food system. Is your home larger? Is the food larger? So if you had to put these in order, which one would you choose? Because you might want to focus on the biggest one, not the smallest one.
Something wrong with C.
Oh, yeah, sorry about that. It's a double. Yeah, I forgot to fix that. I noticed that too, and I was like, oops. Well, choose one or the other, but don't choose both. So about a third of you, now you are knowledgeable people, you really care about this, but you probably never just sat down to look at these numbers, right? Okay, so the winner is it's your home, then it's your car, then it's food. Okay, do we agree now education is important in this space?
But in Santa Barbara, everybody lives.
Yeah. Now these are national averages, because I can assure you that things are different in Pennsylvania than they are in Santa Barbara, right? So I'm not picking on you personally. You'd have to work it out, but it is worth working out. I can assure you that where you live in the country impacts this. Okay, so on average, a person in the US uses 1.25 gallons of gas. Do you use 1.25 gallons of gas every day? Probably not. It depends. Now in Pennsylvania, I can assure you people who are driving these large trucks commuting into State College are using more than a gallon of gas a day. But looking at the carbon emissions here, you've got 12 for that little over a gallon of gas. You've got 8 for the food. Home electricity, 5. So that's based on grid. So again, let's reflect on those numbers relative to some of these country averages. 49 here, India 5. If I now look at these 3 things in the US, we've got 26C. All of China is at 23C. India at only 5C. So these 3 things, our home energy, how much we've insulated, how much we use, our food, what we choose to eat, and whether we choose to drive or not drive, or bike, or use an EV, those all figure into this. So let's think about the pie now, really more about our personal use. So just based on these 3 things, and look at how we can change this breakdown. Now, food's a mixture of fossil fuel direct and then electricity, which then has fossil fuels embedded in it as well. So it's, you got to break it down. Look at car choices, right? So for the students, you're poor, you can't afford a new car, you get out, you go, I'm getting myself a new car. What am I going to get? Well, my son told me he'd never drive my Prius, so he was not going to be in the Prius crowd. But, here's some options. So, give you couple guesses on this one. What emits more CO2 per mile, the Toyota Prius hybrid or a Tesla Model 3? Tesla Model 3 powered by the grid, average grid, not your home, not, sorry. I know the answer if it's your home. And you're thinking, is this a trick question? He's been trying to be tricky in these past ones.
Oh, it's more.
More CO2.
There's a lot of baggage at the top.
It's close, but grid energy, grid electricity, again, it depends on the power plant. But yeah, the Prius is emitting more, and it also has a combustion cycle, which has air pollution impacts and other things that go along with it. But, we limited the question. And again, this is based on...
You didn't put in like one of those big trucks and it's driving to campus.
So let's look at the Ford Lightning EV.
Okay.
And look at a Camry internal combustion, a Camry hybrid, or the Prius or the Tesla. And, so you think you're doing a good job, right? You get this EV, but at 68 miles per gallon equivalent, that's putting out 10C. If you're down here with this Camry, that's about 7 or 8. It's just a little bit worse than the hybrid. But at Tesla, you get down to 5C. And if you charge it off your home, almost nothing. Now, it depends where that electricity came from. So it's going to greatly matter during the day. Do you charge it? Do you charge it at night? If you're in China and you said the Tesla uses more, you're right. Based on the China grid, you're using about 7, or you're using almost 8C, where in the Prius is using 7. And if you run it on a high efficiency natural gas turbine, these things achieve about 60–65% energy efficiency. And so your carbon emissions with that Tesla go down even further, and then of course to 0 if you charge it off your roof. So we're also faced with maybe just trying to put into perspective the amount, the mass, the weight, this gigatons. How do we relate that to other things? Again, we got to be able to relate to what's 1C or what's 2 pounds of CO2. So let's think about solid waste, which we have a massively engineered infrastructure across the US. collect the solid waste, sort it, compost it, burn it, landfill it, whatever. But, we don't have an airfill. We have a landfill, but we don't have an airfill. Or maybe we have a very distributed one. So about half of the stuff we put out on the curb, again, national averages, it's about 14 pounds, 7 kilos. If you're burning 1.25 gallons per day of gas, you're putting out, at the end of the week, about 200 pounds of CO2. Imagine you got 2 cars now and you're pulling out 400 pounds of CO2 to throw away in that landfill. And all the things we do with just the 14 pounds of solid waste. So one solution to all this is not to make you pay for the CO2 capture. Is to have you pay for the CO2 capture rather than the government. So let's just build it into the price of a gallon of gas. And so we could do that. Of course, the price would go from $3.50 a gallon to $12 a gallon. What do you think would happen to anybody who passed a law saying that we're going to raise the price of gasoline to be $12 a gallon so we can run a CO2 capture plant? Good luck with re-election. All right, then another one here is the food you eat. Some of you know this about carbon emissions for certain things, about the food you eat. I'm going to recast it again in C values. Because you say, I save CO2 by eating this, but how much? How does that relate to the CO2 you emit and the CO2 that went into preparing that food? So this is the amount of CO2, not that you breathe out, but the CO2 that goes into putting the food on your table so you can eat it. And it's prepared on the basis of kilograms of CO2 per kilogram of food. So you can look at something like beef here, about 100 kilos of CO2 per kilogram of food. Poultry meat, about 1/10 of that. Then you go further down. From here, you can get down to bananas or milk. Now, this isn't an environmental impact statement. There are other things that go into this, but just that. And let's recast it now to say a food choice you make in C units. Because I'm trying to, that's one way to look at it, right? How much C per day? If you're eating that beef, you're up around 6 or 7 C. If you're eating shrimps farmed, you're down around 1 C, and then tofu's down here. So when I've taught this class and when my colleagues have taught this class, we go through this and we say, okay, if you eat an Impossible Burger or a Beyond Burger, you're at about 0.4 C. If you eat a beef burger, you're at about 6 C, not even talking about the water. That's a huge difference, right? So how many of you, based on this slide, are going to go home and buy an Impossible Burger and try it? Oh, I see.
We already did.
There you go. How many have tried it?
I like it,
All right, good. Okay. Very good. Better question.
but it's never going to replace that Whopper.
That would be impossible. So, when I did this in Pennsylvania, somebody said, well, I understand this, but we have cows, and we like to eat those cows. And so it's important because, that's local cows. That help takes the edge off of this. And I'll get to that point in a second. Just showing you some different, I eat a lot of fish. So, thinking about, is it wild or farmed? By the way, farmed scallops are just really low on the carbon emissions. So I'm not saying eat scallops every day, but eat scallops once in a while. This is pretty good. These farm things, they're really easy to grow. They just pull stuff out of water, quite good. Farm salmon, you could say there's other environmental effects, but in carbon emissions, farm salmon goes way down. So there was, I thought I had one other quiz there. I took it out there. So remember that kid that said we grow our cows? Where's the transport? It doesn't matter. It's all those greenhouse gas emissions, the burps, the methane emissions, the land use, and all that stuff. It doesn't matter whether you get that beef from a long way or a short way away. Its carbon footprint is really set. Now, for other things, it would. For things down here, the transport can be an important component, but not for beef. Okay, so I'm about done here. I'm going to go through a bunch of slides really fast just to kind of give you the subliminal advertising. No, I'm just going to go, part of the things we talk about is what do we need to do to start to lower these numbers, Get used to solar everywhere, over your parking lots, over your stuff by the side of the road, and maybe dividers between the road, over ponds, photovoltaics, over canals. People have done demonstrations, sidewalks. I don't know how durable or economical that is. Agrivoltaics, maybe where the sun is sometimes too bright to really grow certain crops, actually a little bit of shade will be helpful. Marginal lands. People say, well, I don't like to look at windmills. Well, nobody's living here. They don't have to look at them. I don't know if I'd go that far in solar construction. That's an artsy building, but if you want to do art, maybe just do solar art. So now I said I'd come back to this thing of energy use per person increasing. Now that I've taught you about D, I can tell you that energy use per person is increasing about 4D over the period 20 to 25. But renewable energy increase over the same period was only 0.3D. So yeah, renewable energy globally is going up, but it's not going up fast enough to compensate for the increase in per capita energy use. And that's a challenge because a lot of people that don't have enough energy want more. But a lot of people that have a lot of energy are okay. I mean, the electricity use in the US really isn't changing much. Again, the steel infrastructure, how we build buildings now, we don't build them out of stone anymore, we build them out of concrete and steel. That concrete, the only way to get there is through not just one thing, but it's all these different things that we have to do and how we make cement and put it into concrete. If you look at heating water, pumping water, moving it around, that's about 13% of all primary energy. That, of course, is tied in with food in many cases as well.
California's closer to
20%.
20%.
Yeah.
19 to 20.
Yeah. Power plants for wastewater treatment plants. I mean, maybe you just power the local plant or other places or use microbial fuel cells, but that's a whole nother conversation. You can look also at reforestation. It's 15 trees for just one C, so that is a lot of trees. A lot of states don't have that, and the problem is it's not, in these days, it's not very necessarily permanent when you have those trees. And so, we look at climate policy. That's, again, where I started. We need the education. That needs to translate into workable policy by people who will accept those policies. And we need to think about locally and nationally and globally environmental and climate justice. This is not impacting everybody the same. Just 12% of India has air conditioning, and they have some of the hottest temperatures in the planet to get through. We have these nice, well-insulated houses, but we also have other older infrastructures that need this as well. And trees are often a sign of wealth. They're a sign of affluence. So the rich neighborhoods have lots of trees and don't heat up so much, but we're not putting in trees into necessarily poor neighborhoods. So there's a lot of social and environmental justice. And then I have one final question, just for fun. You got to answer this one, because how many sticks of butter equal one stick of dynamite? This is just for fun. less than 1.
Hmm. Oh, we might hit one. Wow.
I love it. So does seeing those affect your response at all, or do you, you know?
Wow. I was wrong.
That's why it was fun. In fact, I was reading an article in Nature, and it said, well, that's equal to about, 3 sticks of dynamite. I'm like, that can't possibly be true. And I vastly underestimated it, just like many of you. Yeah, I think butter is just biofuel. It's like, vegetable oil, diesel fuel. It's actually pretty energy dense. The thing about a stick of dynamite is it takes all that energy and compresses it into a very, very, very short amount of time.
Yeah.
And so, yes, of course, we can reason it out, but that was why it's a fun question, because you just don't think, oh my God, I got 4 sticks of dynamite in that in my freezer. Thank you. And again, reminder on the course materials, or just to learn about this, I've shared that with Eric. He has a USB stick. He can just give it to you and, yeah, buy, steal, or whatever. I don't care. I'm not trying to make money on the book. But anyway, if we have time for a few questions, that'd be great. And I don't want to hold you late if we don't, but thank you very much.
Questions for Bruce? Yeah, go ahead.
I'm very new to the energy space.
Uh-huh.
Did you come up with DNC, or is this a thing that other people are dealing with?
It's me.
Okay.
Yeah. Because I just tried to explain things to people, and I could never, I don't know what a BTU is. So I said, all right, we got to figure out some way around this. So it's something I'm trying out, and we'll see if it catches on or works or whatever. But I think I think you'll walk out of here, you won't think about energy the same way as you did before you walked in here, because you'll now have that number. Yeah.
Steve, how much room do you think energy efficiency can improve on climate change? You showed some models, but
Yeah.
you're real, can it just flatten it out but never reduce it, or can energy efficiency do more than that? Or do we really need to get to photovoltaics and renewables?
It depends what temperature you want to get to when. It's inconceivable to me that we can totally get rid of fossil fuels. It just doesn't seem to work. So the question is, how much of this do we live with? And energy efficiency is the single easiest thing to do that doesn't change your lifestyle. You just insulate your house better. Doesn't, affect how comfortable it feels, but it saves a lot of energy for that. And likewise, driving a car that gets 50 miles per gallon versus one that gets 25 or 20, that's really easy. Or, the EV. Or when you buy a house, you look at that house and you go, oh, look at that roof line. That'll work well for solar panels. Those sorts of decisions, or future houses when you build them, they got to be pointed the right way. So I think there's a lot of easy stuff here that could be a big chunk.
So thinking about your answer to that question, like you were saying, a lot of these things come from our individualized energies, whether it be home, food, etc. How, especially tying back to this environmental justice aspect, a lot of those decisions that you were just talking about come from kind of a very privileged stance of being able to buy the more expensive but more efficient car, be able to insulate your home. How do we empower folks who aren't as affluent to be able to make those decisions that are so important for reducing energy use?
Well, I don't want to make it political, but part of the Infrastructure Act was to see that renewable energy, people in poorer communities have access to both renewable energy and insulation programs. So that's one way you do it. You bring those services into communities, and you volunteer, or not volunteer, but you provide the funding for people to go in and do simple things, very simple things oftentimes, to make those changes. And you're totally right. So many of these solutions are very capital intensive. It's one thing to say, okay, get a a heat pump, don't buy that electric baseboard heating. But that electric baseboard heating costs $100 and the heat pump costs $5,000. That's a big difference, and you don't have the ability to do that. So there have to be programs which allow people to buy a heat pump. The government pays for it, and you pay back, in terms of your monthly electricity, the differential between what the electricity company charges. So it is very, very unfair. It's like when, well, I won't go on. It's unfair, and we need to figure out ways around it.
So I have a question for you.
Yeah.
So, in your C calculation, does that also include M, the methane, there's other, greenhouse gases, like methane's the classic example, right?
Right.
Where, so is it really CM, but you call it C for
I-
convenience sake?
yeah.
Or is it, that's a separate measurement that maybe we should refine your C to include M or whatever?
Yeah, it's a really good point, because by using just it's only fossil fuels. It's just oil, natural gas, coal, and those energy things. It does not include methane emissions, land use changes, and these other things. So and those can be very, very.
So your beef numbers, for example, would be, if M was included, would be even worse.
No, in that particular case, it was in the food. Yeah. Just looking at the food from that situation. In the other calculations I did, sorry, there's a lot of math in there. In the other ones, it just goes into, it actually goes back to a report by Canning et al. And the USDA when they did an analysis of the CO2 emissions arising from the food chain. So some numbers are hidden in there, some are not. Yeah.
So there's another question out here, sir.
Yeah.
I was wondering how you think about kind of comporting these rational approaches to thinking about things versus the emotional decisions that people make on an everyday basis. Are we worried about converting these in just D and C numbers that are, a little bit more intuitive, when are they really influencing decisions that aren't rational, aren't logical?
Well, that's sort of why I raised the calorie thing, because you want to say I'm gaining weight, but you don't look at calorie labels on what you're eating. So there's a disconnect there that you don't want to pay attention to it, or it's too hard to add up all those calories over the day. So, and then you also have the psychological response. If the Democrats think that C values are good, I'm going to think they're bad. So there, you build in that sort of, so it's, I'll turn that part over to the social scientists, but what you're saying is exactly right. You're going to make decisions whether they're logical or not logical, and just your preference. I don't like Impossible Burgers. I like beef, or I'll use turkey when next time I make a taco instead of beef. Okay, well, it's like, I don't care. Once I put a lot of taco sauce on it, who can tell?
When you're making the 15 tree comparison,
Speak up a little bit, so.
Yeah. 15 trees.
15 tree comparison, what size is the tree?
It's an average. So I read through a lot of different literature about, how many trees per acre. It's like 100 trees per acre, and on average, it's over sort of the growing cycle. And you're taking into account trees falling down and new trees growing. So it's one of the things you struggle with is want to be scientifically accurate. Is how do you balance really fairly representing what's going on with, okay, it's 15 trees, right? So 15 trees, you get it. If I said, well, that's 5 young trees and 15 mature trees, and it's like, okay, 20 trees, I'll take it. So yeah, it's a balance. And it's based on really per acre and how many trees you have on average per acre.
You got another question or two?
Anything else? Sorry, I'm holding you here, so.
Okay, let's give our speaker another hand.
All right, thank you.